Good afternoon, morning, or evening to all of you, and thank you for registering and joining us to this live webinar. So my name is Justin van der Hoofd from the Glasgow Polyomics at the University of Glasgow in the United Kingdom, and I will be hosting this webinar today on behalf of the Early Careers Members Network of the Metabolomics Society. Actually, this is the 8th in a series of webinars and is brought to you by the Early Careers Members Network Committee. Currently, the webinars are free for all to attend by the courtesy of the Metabolomics Society, and I would like to inform you all that all the material will be recorded and uploaded to the Metabolomics Society website, allowing access to the live content at your own convenience. There, you can also find all the past webinars. So please connect to us using Facebook, Twitter, LinkedIn, as shown on the screen. And I would also like to ask you for feedback about the EMN. You can share your ideas and suggestions at the email address on the screen now. So before introducing our speaker, I would like to remind you that at the International Conference of the Metabolomics Society, Metabolomics 2016, in Dublin, at the end of June, the EMN committee is hosting a welcome social mixture on the 26th of June, the Sunday, 2 workshops on the 27th of June, a reception on the 28th of June, and we will be chairing the Young Scientist talk sessions on the 29th of June. More details about the 2 workshops will be given later after the webinar. Today's expert speaker is Dr. Jan Stanstrup, actually also a member of the Early Career Members Network Committee. After a master thesis on identification of natural products by NMR, Jan Stanstrup moved into the field of LC-MS-based metabolomics under the supervision of Professor Lars Dragstedt, where, while working on several nutritional metabolomics datasets, he developed a semi-automatic pipeline for compound identification in collaboration with Stefan Neumann. In 2014, after obtaining his PhD from the University of Copenhagen, he won a grant allowing him to continue with his passion in creating tools for compound identification, and he developed a public platform, PredRat.org, that enables retention times to be transferable between laboratories and LC conditions. Today, attention will be given to that during the webinar. Currently, Dr. Jan Stanstrup is employed in the Systems Medicine Group at the Steno Diabetes Center in Denmark, where he works on data processing and data analysis in addition to compound identification. Dr. Jan Stanstrup, as I told you in the beginning, is also serving on the EMN committee since October 2015. There will be time after the webinar for questions, so please send your questions by using the questions options of your webinar application. You can type the questions throughout the presentation and our speaker will answer them live at the end of the webinar. If there are many questions, I will select a few of them as we don't have time to go through all of them. I think we are ready to start, and I will pass you on to our webinar speaker of today, Dr. Jan Stanstrup.
Thank you very much, Justin, for the nice introduction. So I will get right started because we have a lot to cover in this talk that hopefully should show you how you get from features in your peak table to real compounds. So with this webinar, we want to try something a bit different than the other webinars. Here, the target is really researchers with no or very little experience in compound identification. That also means that if you have questions, then it's fine. No question is really too basic, so please post your questions. And we will try to make this talk a bit more tutorial and course-like than what we have had before. So of course, compound identification is a very large topic, and you won't become an expert in 40 minutes, and this talk, of course, won't cover all nuances to compound identification. But hopefully you will know how to get started. So the agenda for today's talk look like this. We will spend quite a lot of time on molecular formula because that is really the basis of compound identification. We will look at how you find the so-called pseudomolecular ion, and I will get back to what that means. Then, once we have a molecular formula, we have some databases we can use to propose what the structure of the compound is. And finally, if there's no obvious hit in the databases, we can start looking at the fragmentation pattern of the unknown we want to identify. And finally, we have also retention time that, in addition to the mass spectra, can be quite useful in identification. Finally, we arrive at the point where we need to report our results, and we will discuss a bit how to best do that. So first, let's remind ourselves where we are in a metabolomic study. A pipeline could look like this. If we have, for example, a nutrigenomics metabolomic study, we can have a meal study where we take some samples. The samples are analyzed on an instrument. We get some raw data, and we then use some software that pre-processes this raw data into a peak table. So we have a list of features. We then do some statistics that tell us which of these features are interesting in the context of our study. And now we have arrived at the point where we will be talking about today. So here you can see I have put identification and interpretation together because these are very much tied into each other. So that's also why I think it's very important for everybody, even if you're only working or mainly working on the biological aspects of the study, to have some idea of how the identification is done. Because without identification, you cannot put your results in biological context. And just looking up a mass in a database is not enough. And that is why this piece of identification most often becomes the most time-consuming part of the whole metabolomic study. So, the first thing we want to do when we want to identify something is we want to find the molecular formula of the compound. So the basic question we are asking is, we have some mass and we want to know what does this mass represent. If we were to do this manually, we would sit down with our list of elements and we need to make some combination of atoms that in the end have a mass of 46. You could of course also ask a computer to do this, and it will give you a list like this. If you look down the list, you will see that there are some suggestions that are not possibly chemically. For example, we have hydrogen 14 and a sulfur. This is cannot exist chemically. But at least in this list there are at least 3 real compounds that exist. So we would also like some additional tools to then distinguish these. In this case, probably the mass difference is big enough that by the mass itself we would be able to tell the difference. But as the mass becomes bigger, you will have several real molecular formulas so close in mass that you need other things to tell them apart. You can also see that in this list I've added some extra information. We have a nitrogen rule and double bond equivalent, and I will come back to what they mean. Because now we had a list of every possible way to make a certain mass, but not all of them are valid formula. One way to remove formulas that cannot exist in nature is to use the so-called nitrogen rule, which states that for organic compounds that contain the most common elements, a compound that has an odd nominal mass has an odd number of nitrogen atoms. And I don't think there's any clever reason why this is. This is a consequence of the number of bonds the atoms make and their mass. So conversely, an even nominal mass compound has 0 uneven number of nitrogen atoms. We need to be a little bit careful with this because when we actually do a recording on our instrument, if we do electrospiralization, we will either add or remove a hydrogen to the compound, which means that the mass changes by 1 and then this rule above will be reversed. On the other hand, if we do electron impact, like in classical GC, only an electron is lost, so there the mass doesn't change. We should also be a bit careful when the compounds become a bit bigger because as the mass of the compound grows, the non-integer part of the mass, so you have a mass that is something, point something something, the something something eventually adds up to 1 unit more, and then this rule breaks down. But it's a very useful rule to remove formulae that are not possible. Then we have the double bond equivalent, and it has a number of synonyms I've written here. And what it does is if you have a certain formula, you can calculate how many double bonds should then be in the compound. won't go through the calculation, but the way it works is that if you have one double bond, that adds 1 to the value, a triple bond counts for 2, and a ring counts for 1. And then you have benzene ring that since it has 3 double bonds and a ring that counts for 4. So there's several ways we can use this. For example, we cannot have a negative number of double bonds. That doesn't make any sense. We also cannot have half a double bond. And in addition, you see the benzene ring has a double bond equivalent of 4, and so if you have a very high double bond equivalent, that is a good indication that you have a benzene ring in your structure. Again, here this rule needs to be used carefully because there are some atoms, like for example sulfur, that can make different number of bonds. So in this example we have methionine, but it can be oxidized in different places and making different amount of double bonds. But if we do the calculation above, all of these formula will give a double bond equivalent of 1. So useful rule, but again need to be careful. So now we have looked at what we can do with just a single mass. But we have much more information in the spectrum. And some of this information is the isotopic pattern. So the isotopic pattern arises from the fact that most atoms can exist in different isotopic states. So for example, we have carbon, where the most normal is carbon-12, and on Earth we will have about 99% of all carbons be carbon-12. And then 1% is carbon-13, meaning they have one extra neutron and they therefore weigh one additional mass, unit mass. We can use that because if we look at a formula like this, for example, we have 6 carbons, 5 hydrogens, and a chloride. What we actually see in the spectra is not a single mass. What we see is something like this. We have what we call the monoisotopic mass, which is the peak equivalent to where all the atoms in the molecule is in the ground, or the most common isotopic state. And then we have additional peaks here. And this pattern is then unique to each molecular formula. So if you have a mass where you don't know if it's one formula or another because both have very similar mass, you can look at the isotopic pattern. That might be different enough for you to distinguish them. So if we look at the first one here, we can then look at how do we figure then the relative abundance that create this pattern. And we can do this because it becomes more or less just a question of probability. So we know we have 6 carbons here. We know the probability of a carbon being a carbon-12. Over here we have then the probability of the hydrogen being hydrogen-1, and we have 5 of those. So we know that about 71% intensity should be the monoisotopic peak, and we can then do that for the other peaks. Again, we have now 2 ways to have a +1 isotope. It could be that it is the carbon that have an extra neutron, so then we have 1 carbon-13, and we can calculate the probability of this combination of atoms. But it can also happen in another way. That could be that it's one of the hydrogens that have an extra nitrogen. We can calculate the probability of that at the probabilities, and we get about 5%, and we see a peak here, 5%. And we can continue doing that with the next isotopes, but obviously this becomes quite complicated and time-consuming, so we will use some tools to look at this, and some of the tools are linked down here. Yes, but if you have access to an Orbitrap instrument that have very high resolution, you can actually see even more on the isotopes. So the peaks we looked at before, there was just 1 peak for each isotope. But if we have high resolution enough, we start seeing several peaks. And that is because adding a neutron to different elements actually doesn't change the mass by exactly the same amount. So we have a peak here for carbon-13, but if you have a nitrogen atom, you will see a separate peak for the nitrogen. So this is very useful to tell you the molecular formula, because if we see a peak down here, we know that there is a nitrogen in the compound. Good. So now we would like to do this a bit more structured and automatic, and there exist many tools for this. One of them is this. It is linked down here. It's a tool that I have put together, where you can put the mass you're interested in down here. If you think you have some kind of adduct, and I will come back to adducts in a moment, you can select that up here, and it gives you a list of all the possible molecular formula with this mass. You can then click on the suggestions here, and it will give you the simulated isotopic pattern over here that you can then compare to what you see in your spectrum. Down here you can find some additional filters. So for example, if you know that you have a nitrogen in the compound, you can put that down here, and it will then only tell you the formulas that actually contain one nitrogen. And there are some additional filters here that I won't go through, but I suggest reading the paper from Oliofine's group that talk about 7 golden rules for molecular formula. So, but before we can actually start finding the molecular formula, we need to be sure that we are looking at the so-called pseudo-molecular ion. So I will just explain what the problem is. So if we have a standard MS1 experiment, it looks something like this. Your compound elutes from the LC column, then it gets ionized in the electron spray ionization in the quadrupole and the collision cell. Nothing really happens in the MS1 experiment. But then the compounds are isolated by mass in the top, they hit the detector, and you get a mass spectra down here. So in an ideal world, you would get one peak for each compound. Unfortunately, that is not what happens, because the compounds actually start fragmenting already up here in the source, and that's why they're called in-source fragments. So you can see I've shown that down here with the green compound. We have the whole molecule down here, and that is what we call the pseudo-molecular ion. Molecular because it's the molecule, pseudo because it has been charged, so it's no longer in the form that it actually was in your sample. Of course also ion because it's charged. And then we have a fragment of that compound here. And if you look at the spectra, we can see that that fragment also gave us a peak. So unfortunately, your mass spectra does not come color-coded like this, so we would like some way to figure out which of the peaks in your mass spectra actually belong together. And I will come back to how to do that. But one other thing can make this more complicated, or can create additional peaks in the mass spectrum, not only fragments. We also have adducts. So normally, your compound is charged by a hydrogen being added or removed to the molecule, but it can also be charged in other ways by adding with, by combining with, for example, sodium, potassium, or chloride. You can even have neutral adducts, so the molecule might be charged with a hydrogen, but a formic acid was also attached, or even a salt molecule. So in these plots, I have tried to take a whole study and see what kind of adducts and fragments was actually found. And you can see that the most common ions you would see are the pseudomolecular ions. But it's actually just a relatively small fraction of all the features. In positive mode, you very commonly see the sodium adduct and the potassium adducts. Water loss is very common, and so on. In negative mode, we have the chloride adduct that is very common. And we actually also have sodium adducts, even though that is something you usually associate with positive mode, that is also relatively common in negative mode. And in that case, we need to remove 2 hydrogens from the atoms to have a species that is in the end negatively charged. And you also actually see some very exotic species like this dimer with an iron. So finding this manually again is very tedious work. So luckily there are some tools for that I will show in a moment. But let's take a look at what these adducts actually look like in the spectrum. So in this case, the biggest peak here is the pseudomolecular ion. And then we will have down here the adducts with a higher mass. So in this case, we actually don't find the most common adduct that we would have expected. We would have expected to see a chloride adduct maybe. But what we see is something else. We see something that you can see I have written here 2M, and that means that two molecules went together and was charged as one. So you get double the mass. We call this a dimer, and you can see we also have a trimer down here. And one of these dimers was also made an adduct with sodium, and since it was negative mode, we removed 2 hydrogens. So a lot of different adducts can be found. Then you have peaks here that, since this is an MS1 experiment, we are seeing everything that is eluting from the column together with the compound you're interested in. So in this case, we have some contaminants, and you can realize that if you take these ions and do the extracted ion chromatogram, you will see that they have not a nice peak like the compound you're looking at, but a constant presence in the whole chromatogram. So they're clearly contaminants. Then you have other peaks that at least I was not able to explain what are, so it could be that it's adducts that I don't know about, or it could be that it's a compound that just happens to be eluting at the same time as the compound I was looking at. But here it's also again important to actually look at the extracted ion chromatogram and check that they are eluting at exactly the same time as the compound you're interested in, because if you're just looking at these from your peak table, they might have so similar retention time that you don't really see them as different. But again, doing this manually is very tedious work. So now help is arriving, and it is arriving in the form of camera. That is a very nice tool to try to do some of these things in an automatic way. So what we're looking at here is a normal peak table where we have the features that have a mass, a retention time, and then what camera does is it's trying to say which of these actually belong together, coming from the same molecule. And in this case, camera is saying that these are from the same molecule. And it is then adding additional information. It is, for example, saying that this one is the one with a mass 166 is an isotope of the 165. Very good. Then it's also adding information about the adduct. So it is saying it thinks this is the sodium molecular ion because that fits then with this being a sodium adduct and this being a dimer. And then we have the fragments here that it is suggesting. So in this case it works very well. We have every feature accounted for, either as an adduct, an isotope, or a fragment. Unfortunately, it doesn't always work out so well. Often you will see several compounds put together if they are very closely co-eluting and also somehow correlated across samples, then camera is not able to distinguish them. Also, this annotation you get is heavily dependent on what adducts and fragments you tell camera about, so it can only annotate fragments that it knows exist. So here down here I've put a link to the fragment list I'm using that you can use. So camera is made as a kind of add-on to the program XCMS, that is a program or a R package that you use to pre-process your raw data. So if you're, for example, instead using MZ9, they have implemented the camera, but they have not implemented all the features. So I've created a function that you can use to convert your MZ9 peak table to an XCMS object that you can then run camera on and get this kind of annotation. So now we have arrived at the point where we have some idea of what the molecular formula of the compound is, and we want to figure out then what is the structure. And the first thing we should then do is look in the databases of compounds that are known to exist, see if in the context of your study there is something obvious that this could be. So this is not because you should assume that a hit on a database means that you have identified your compound, but it's a lot easier to confirm a hypothesis that it is from the data from scratch to come up with a hypothesis for the structure. So the databases can roughly be divided into 3 groups. We have the big ones, the more global ones that try to collect every compound that have ever been reported, and then we have more focused ones that might be specific to biologically specific, so it could be compounds that have only been reported in humans, for example, or it could be specific to a specific compound class, and those databases usually then have more information about each context of each compound, that will help you decide which of these compounds is most likely in your case. Then we have the spectral databases that don't contain only the structure of the compounds, but contain actual spectra of authentic standards that you can use to compare to the spectra of your unknown. So now I've put it in these three groups, but a lot of the databases is kind of a mixture of these three groups. So if we look into specifically databases are useful, one of the ones is human metabolome database. So if you're using human samples, if you have human samples, this would be your go-to database. Then we have Medlin. That's also a good database that also contains some mass spectra. Actually, human metabolome database is also starting to have quite a lot of spectra. Then we have lipids. If you're working with lipids, for phenolics we have Phenol Explorer, and then there's CEPI that is kind of a mixture between these types of databases. It is quite large, but it is humanly curated, and you have some information about each compound. Then you have the big ones, that is ChemSpider and PubChem, and you have the mass spectral databases, where MassBank is probably the biggest one, and then you have MSTED Cloud, that is a very nice database, but quite Orbitrap-centric at the moment. But if you have an Orbitrap, this is probably your go-to database. So again, for the moment we have only used information really from a single mass. Now we need to start looking at the fragmentation pattern of the compound. So it could be there was nothing obvious in the database where you could just go out and buy the standard I compared to, or maybe there are so many hits in the database that you would like a better idea of the structure of your compound before you start investing in standards. So what you would normally do is a so-called MS2 experiment, where your compound again is eluting from the column, it gets ionized in the source, but then in the quadrupole, the specific compound you're interested in is isolated, and then in the collision cell you bombard the compound with some inert gas that makes it the compound fragment. Again, they hit the detector, and you get a spectra with only peaks related to the compound you are interested in. So in this experiment you might have to play a bit with the energy of the collision cell, because some compounds fragment at very low energy, some need a lot more energy to give you any useful fragments. So a spectra will typically look something like this. So what do you do now? You have a spectra and you need to figure out what can the structure be. And to do this manually, you again start looking at the differences between the peaks. So down here we can see there's a difference of 18. And if we look that up in a table, which I will show in a moment, we see that that corresponds to a water molecule. Okay, that is not the most useful fragment, because every compound that contains oxygens more or less will show this kind of fragment. Then we have another fragment up here, a CH4 sulfur. That's much more useful, because this is not very common to do this kind of fragment. Then instead of looking just as the differences between the pseudomolecular ion and a fragment, we can also look at the difference between fragments. So here we can see that this corresponds to a loss of an acid group. Good. So now I just wanted to show you one of the resources I'm using to look at these differences, and one of them is from the supplementary material of this paper. That's a very nice list, both of fragments and adducts that you can use. Then there's also a table from this nice book where you have more fragments. Unfortunately, they don't have the accurate mass, so only nominal mass, and you will have to calculate the accurate mass yourself. But they also give you some hint of what kind of compound class you are looking at. So if we go back to our spectra now, we arrive at a point where we find a peak where we see a loss of NH3 and an acid group. So now we can start thinking, if we have an amine and an acid, maybe this could be an amino acid. And we also saw sulfur up here, so there's not that many amino acids with a sulfur. So now let's try to look at what the molecular formula of this fragment could be. We get a formula like this. If we look it up in a database, that happens to be methionine. So lucky that in this example it works out quite nicely. Then we will take a look at then what is there more than methionine. So we look at the difference to the peak that correspond, or we think for the moment correspond to methionine, and we look at what is then left, and we get a molecular formula of 8 carbon, 6 hydrogens, and an oxygen. and we calculate the double bond equivalent and see that the double bond equivalent is 6. Aha! This is quite high for something that only has 8 carbons. So probably we have an aromatic ring. So an aromatic ring, 2 extra carbons and an oxygen attached to methionine. Now we come up with some suggestions for how that compound could look like. And one suggestion is this. So we have the methionine here on the right and the rest on the left. So we have our aromatic ring, 2 extra carbon and an oxygen. So from the spectrum, we wouldn't know if this oxygen is attached to this carbon or the next one down here. But this is where biology and identification starts to intersect, because if we think about how this methionine adduct was probably made, probably this happened between by a reaction between methionine and phenyl acetate. So probably there used to be an acid group on this part, which means the oxygen need to be there. We also could not be 100% sure that the oxygen was not somewhere on this ring and then a double bond somewhere down here. But we actually have a fragment that can show us that that is probably not the case. But now let's look at the fragments we observe, see if this structure would explain them. So we start drawing structures like this and see that just by breaking bonds we can explain all the fragments. And we got this piece in the end where there's no phenyl group, no oxygen down here, so probably that means that the oxygen is not on the ring but one of these two positions, and biologically we would think that it's probably in the position I have put it. And then you need to go out and see if you can buy this compound and compare to the authentic standard. So if you were paying close attention before, you saw that I said that this piece had a double bond equivalent of 6. But we have only accounted for 5 down here. We have 4 for the benzene ring and 1 for this double bond oxygen. But that is because what happened when it fragmented was that one of the hydrogens attached up here to the carbon had to go to the nitrogen to create a stable compound that looks like this. So, and the fragment then looks something like this. If there's a mass spectrometry expert listening, he will probably say that this is not the right structure. But the point is that you need to create an extra double bond somewhere in this structure to explain the fragment we have seen. And if we look at a lot of the other fragments, the same is the case there. So again, be careful looking at double bond equivalents of fragments. So this was a relatively easy case where we had fragments only created by just breaking bonds very simply. Unfortunately, it's not always that straightforward. Even with a common compound like tryptophan, we start seeing something interesting. It can fragment, for example, this way, where we have the loss of the NH3. Then we create this unstable species where the oxygen then starts to move. So you see the oxygen has moved from this carbon down here. Then the compound fragments further at this point, and we create a fragment like this. And this is actually a quite large peak in the mass spectra that we would not be able to explain from the structure of tryptophan unless this kind of rearrangement happens. So here the lesson is that even just because you cannot explain a certain peak in your mass spectra doesn't mean that the structure you have is not the correct one. Quite strange things happen in mass spectrometers. And here is an even worse example where we have flavonoids that create a fragment like this. So it's not very obvious how we get this fragment from the structure of the flavonoid. And down here we also get rearrangement of this ring to get this strange 4-membered ring. It's also not something very obvious. So the lesson could also be here that if you're working with flavonoids, you need to know what kind of fragments to expect from this kind of compound. So now we have tried to do this manually, which is a lot of work and requires some expertise. So let's see if there is some tools that can help us do this in a more automatic way. And there luckily we have what is called in silico fragmenters, and some of the first one is these medfrag and medfusion, and what they do is basically the same as we did with the first example. They take all the compounds in some database that have the mass you're interested in, and then they start breaking all the bonds in the molecules to see which compound can actually account for the fragments we actually seeing. As we saw, in a lot of cases this is not really sufficient and not yes, it's not the only thing that can happen in the fragmentation. So there's a lot of development in this area, and one of the latest developments is the CSI Finder ID. That seems to be outperforming the other tools at the moment. Unfortunately, at this point it's only available for positive mode spectra. Another approach have also been made in Lipid Blast, coming from Oliver Fien's group, where instead of trying to explain the spectra of your unknown, they generate an in silico database of mass spectra by taking a lot of lipids and trying to simulate what should their spectra look like. So you then have this database of in silico spectra that you can compare to your unknown. But let's look a moment how you practically use this CSI Finder ID. It's a website, so you simply go to the website, put in the mass you're interested in. You can give it some information about what elements you expect and what kind of ion you're looking at, and then you give it the mass spectra you have observed down here. And you give it in the form that you have first the mass and the intensity of that mass in the spectra, and it draws the equivalent spectra over here. So this is meant to be used with MS2 style spectra. But if you use camera, for example, to figure out what fragment you have from your compound, you can actually use this before going to do extra experiments. And in some cases that actually works quite well. So the next thing that happens is it is suggesting which molecular formula that could fit with the mass. So it's not doing this in a theoretical way like we were looking at before, calculating all the possible formula. It's looking at what formulas actually have been reported with this mass. And you have the suggestions here. But then what it is doing is saying the fragments we are observing also need to be subformulas of the whole compound. So over here, it's explaining each fragment and what the molecular formula is. So you can go through this list and see which of these formula actually makes more sense. In this case, it would be the first one. When you have decided that, you say, okay, then go ahead, then try to figure out what the structure is. Then what it does is it takes all the compounds that have this molecular formula in the databases it's using, and it's calculating which structures are most likely to create the spectra that you have observed. In this case, it's coming back with the structure as the most likely. And you can see it has the name positron, which at least to me was a bit strange, but that happens to just be a commercial name for the compound tryptophan. So that looks good. We have a common compound. But in many cases, it would not be so straightforward. In this list of candidates, there might be several candidates that have more or less the same probability, and we need to figure out then with additional experiments if there's some way we can distinguish them. But it's a very good starting point. So now we have looked at how we can use fragmentation to find the structure of the compound. But we actually know one more thing about the compound. We know its retention time, but it's also specific to that compound. So one way to use the retention time is simply go out and buy standards and see which one have the same retention time. But that could be a lot of compounds that we would have to buy. So we would like to see if we can do something before to exclude some of the possible compounds. And there have been a lot of attempts to do this. There have been, for example, these quantitative structure retention models. The problem with those is that they are specific to the chromatographic system for which they were built. And they are not that accurate yet. But they can be useful. So one example of a simple model of this kind I've shown here, where each dot is a compound. And then we have the experimental retention time over here. And then we have the predicted log D or log P value. And that is something that several programs can do. You give it a structure, and it predicts what the log P value should be. And the log P value says something about how lipophilic a compound is. And lipophility is the main determiner of retention time. So you can see there is some relationship between this predicted value and the actual retention time. But it's not very strict. So we would like to see if there's some way we can do this prediction more accurately. And there have been some systems that try to do this. There's retentionprediction.org where you get extremely accurate predictions, but it requires also a lot of extra lab work. Then there's the PredRed system, that is something I've developed that I will explain how that works. So the idea here was that instead of trying to predict the retention time from the structure, we say that maybe someone else in their system have recorded the retention time for this compound. Maybe we can use that. So again here each dot is a compound, and now on each axis we have the retention time on two different chromatographic systems. And you see here the relationship is a lot stricter. So if we know the retention time then of a compound in only one of these systems, we can then predict where it should be in one of the other in the other system. And we can then do this kind of one-to-one model between a large number of chromatographic systems. So here we have taken a lot of retention time data from our own systems, but also a lot of public data. We calculate these models, and then we can translate the retention time of compounds that was only known in one system to another. And this prediction is quite a lot more accurate than predicting from structure, but of course is limited to only the compounds where someone has reported a retention time. And you can see the results here that, for example, for these systems, a couple of hundred compounds were put into this system and it could get back several hundred predictions. So in this way you can increase the number of compounds where you know the retention time quite a lot. And over here you can see that the accuracy of this prediction is quite high. Good. So just a small example of where this would be very useful. For example, we look up a mass in human metabolome database. It gives you back 4 suggestions. Then if you had known the retention time of these compounds, and that is what is put down here in the circle, that is the experimental retention time, you can see that the 3 isomers down here, they actually have very different retention time, so we would have been able to separate them. Then with this prediction system, the prediction I got is now here in the square, and the prediction interval is this line here. So we can see that unless the retention time of the unknown we were looking at is in this gray area down here, we would have been able to, without buying any standards, doing anything, figure out which of these isomers we were looking at. So now we have arrived to the point where you need to report your results, and you need to say how sure are you of the identification you have done. And for that, about 10 years ago, there was a paper by the Metabolomic Standard Initiative that defined 4 different levels of certainty. So the first level, they say the compound is identified. And for this level, what is required is 2 independent measures compared to an authentic standard. So they suggest, for example, retention time and the mass of the compound. In reality, what you should be doing is also comparing the mass spectra once you have the standard. That is much stronger evidence that you have the right compound. Then you have level 2 identification, that is putatively annotated compounds. And here, instead of comparing to authentic standards, you have compared to some spectral library or some other published data. Then we have level 3, where we might not know the structure of the compound, but we might know what kind of compound. So it could be a lipid of a certain class. Then we report that this lipid of this certain class is what we have, but we don't know the structure. This would be a level 3. And then we have level 4, that is just unknown compounds. So these levels are very good, and you should use them when reporting your findings. But there are some nuances to this. So one problem is that does this MSI level 1 actually mean that you have the structure you say and it cannot possibly be another structure? And in many cases the answer is no, because there will be other compounds that have the same retention time or almost the same retention time and a spectra so similar that you cannot tell the difference. So in this case you could go out and then buy all the isomers if it's possible and come to see if you can actually distinguish them. But having just one standard in this case, if there are similar structures, would not be enough. Then we have the problem that different people could mean different things when they say they have 100% sure ID of some compound. We have, for example, positional isomers. So especially with lipids, it could be that you might know that there is some amount of double bonds, but you don't know where they are. So you need to report that uncertainty. And even if you think that biologically it only makes sense that this double bond is in one position, you should not report the position because you don't have experimental data to show this. You also have some trans isomers that you normally cannot distinguish in an LCMS experiment. So that is also something, unless you have done something specific to tell the difference, you should not be reporting a specific structure. Then in the end we have stereoisomers. So it's well known that we cannot distinguish compounds that are mirror images in a normal LCMS experiment. But you actually also have compounds that are stereoisomers, but not necessarily mirror images. So if you have more than one stereogenic center in your compound, there will be more than 2 stereoisomers, so they cannot all be mirror images. And those different isomers can actually have different retention time. So that is also something to keep in mind. Also when you are buying standards, you might be buying a standard with a different stereoisomer than what you have. You get different retention time and say this is not the structure, but it could actually be. So now we are right at the end for the summary. And so we have looked at the mass and the isotopic pattern. That will help us find the molecular formula, and also the fragments themselves can help us with the molecular formula. Then we saw that not all possible formula that we can make are actually valid compounds, and there were some rules to filter out those suggestions. Then we have adducts that can make it very difficult to find the real pseudomolecular ion. In some cases can actually also help us if we have a whole number of adducts that fit with a certain peak being the pseudomolecular ion, then that is good evidence that we are actually looking at the pseudomolecular ion. Then we have the fragments that give us the structure of the compound. Finally, we looked at some of the databases and the tools that you can use, and I want to stress again that it is crucial that you report the level of certainty in an unambiguous way. So then finally I want to end with a few suggestions that I wish someone had told me when I started with compound identification. The first one is start with low-hanging fruit. So that means if you have a compound to identify, look up in a database first. If there is an obvious hit, it's much easier to confirm that than it is to come up with a suggestion looking at fragments. Then if you don't have enough data in your spectra, then don't waste time trying to identify your compound. It's not possible. So either you get more data, which means probably additional MS experiments, or you accept that you won't be able to identify this compound, and there's anyway so many features in your peak table that you won't identify everything. But it might help continuing in your list of features, and in the broader context of the other identifications you make, you might be able to go back and then have a better idea of what this compound was. Then don't try to identify something before you are quite certain that it's the pseudomolecular ion. If you're looking at an added-on fragment and try to identify that, you will be wasting a lot of time. Then also always look at the extracted ion chromatogram of the feature you are trying to identify. Don't just rely on your peak table, because it might contain things that are not real peaks. So check, do you have a real peak? And if you're looking at fragments, do they actually elute at exactly the same time as the main ion? Finally, don't use the MSI levels blindly. You need to use some good chemical sense and report uncertainty in a very meticulous way. But remember, there's no substitute for using authentic standard, but even if you have them, they might not be enough, so you need to consider that carefully in each specific case. So finally, I have a list of papers that I suggest you can read. The first link up here is to my website, where you will also find these slides so you can extract some of this information. So I think that's it for me, and I will give the word back to Justin, that I think has some more information and might also have collected some questions.
Thank you very much, Jan. This was a wonderful webinar on compound identification from LCMS features. So as promised, I will come back to the Early Career Members Network activities during the Dublin meeting end of June. We will organize 2 workshops. One is focused on career development and one is focused on experimental design as one of the basic cornerstones of a good metabolomics experiment. So for those of you that are planning to come to Dublin, we hope to see you at one of those workshops, and of course we hope to also see you at our meet and greet on Sunday and our EMN reception on Tuesday. So with that, we come to the questions. So we have a question here, which is, how were the frequency of adduct ions determined for positive and negative modes? And I think this relates to one of the slides where you showed an overview of these adducts.
Yes. So I can. Okay, now that's all. So the question is for this slide, how did I figure out the frequency? And of course this is not a perfect thing at all. This is based on the camera annotation. So this is based on the fragments that camera suggested. So there could be a lot of fragments that is not in this list because it depends on the list of fragments that I put in, and of course also camera is not perfect. It can mismatch fragments. So yeah, this is purely based on camera's annotation of a data set I was working with. But it's all, I mean, it shows more or less what you would expect.
Okay, and is it easy to get these pictures out of your data then?
Yeah, if you use camera, then it's very easy. It gives you a list of how often an adduct was annotated.
Okay. So another question is, so how do we know what actually happens in the mass spectrometer?
Well, I guess the question is we don't. It's a bit unspecific question, so I don't know what was meant here.
Well, I think we showed, or you showed, some fragmentation pathways, and we are trying to postulate what happened, but the question is, do we really
it's
know?
more or less it's a reverse engineering task basically, where you try to explain what you actually observe. But of course you can never be sure at all, and the structures I suggested could look very different in reality.
Yes. So, and I think we have another question.
We also have someone with the hand up. I don't know if you want to give the word to.
The hand up.
Yeah, we have an Anas Honoré.
Yeah, I can unmute him.
Yeah.
Can you try to speak up, Anders?
Yeah, I'll try to. Can you hear me?
Yes.
Yeah.
Okay, great. Excellent presentation. The question from me is I saw all these excellent tools, and I assume that you are able to automate several of the steps and use automatic queries. Do you see any potential in sort of making full workflows using, for instance, KNIME or any other support?
I think there have been some attempts on that, but I must admit I'm not very familiar with them. I think also from Alberta they have some tools that try to put things together. But yeah, I definitely see that as a good option, and I think some work has been done there, but I'm not able to, on the top of my head, to remember where they are.
Okay, thank you.
Okay, we have some more questions. I'm still not clear with the interpretation of the mass spectra. Suppose I have a mass spectra of a crude plant extract, then I go to the database and try to find out what each peak represents by typing in the mass to charge ratio, and then 1,000 possibilities pops out. How do I choose the appropriate one in terms of annotation?
well, you would need then to start looking at the fragments. If there is some part of the structure that should give different fragments, but I mean you're working with plants, so of course it can be very difficult. You also have the problem that they might not be in the database in the first place. So again, it's a matter of you need to look at the individual fragment pieces you get and kind of work your way back. So if we have this example, you might start at the smallest peak you saw and see that we have this kind of fragment, and then from this you might go to this one and say that then we have some additional carbons and our nitrogen, but in this case it would be very difficult to say exactly where things are. But you are perfectly right. At least I don't have the good answer of what exactly you need to do, because it's a question of generating hypotheses, right? For example, if you have these flavonoids, they can have the oxygens in different places, right? So if you see over here a fragment where, for example, the mass does not account for an oxygen here, but otherwise you have this fragment, then you know that if the whole piece had the same mass, but this fragment doesn't account for an oxygen here, then the oxygen must be somewhere else, for example, on the other ring up here.
Okay, and maybe I can
But
add, Jan.
yeah, maybe you can add something.
So I think it's also good to ask yourself the question which database you're looking in, as if you would take PubChem, it will give you indeed very, very many possibilities, but many of them are also really, really unlikely in view of that, for your type of sample. Say that you find some sort of drug in your grass extract, then you have to ask yourself the question how likely is it that you find that specific drug in your grass extract. So
exactly. So that's also what I try to say with biology really intersecting with identification, that you really need to be aware what you would expect in your sample. That helps a lot.
Exactly. So a few more questions, Jan. So you've pointed out some shortcomings of the MSE identification criteria. Thus, what would you suggest for the criteria of level 1 compounds?
Oh, yeah, that's a very big question.
Well, give it a shot. I mean,
well, I've been thinking a lot about this, and there was also a recent paper by Lloyd Sumner where they came with some alternative suggestions. I don't think we have the answer at the moment. I mean, one solution would be if you would be able to specify a structure including the uncertainties. So as far as I know, that doesn't really exist. You have in a computer readable way, right? You could have a structure where you define a lipid, for example, but not where the double bond is, just that it's somewhere.
Mm-hmm.
At least for computers, then you could have something computer readable that accounts for your uncertainty. And yeah, also in classical kind of handwritten ways, there's also ways to do this notation, but I really don't think that we have at the moment the answer for how to report this in a simple way with these kind of levels. So to me the answer is that if there's any doubt if it's one structure or another, you should report that in supplementary material or otherwise, explain what you did and what the uncertainty in this is. So it's just be honest with the identification you have done.
Yes. So a few other questions. Thank you, Jan. I think that we haven't heard the last word on this discussion in the Metabolomics Society. So how different are the fragmentations of different adducts of the same molecule?
Yeah, I've never looked into that. I cannot answer. I would expect them to be quite similar, but I think you can also have unlikely cases where you have adducts of fragments. Then it becomes very hairy. But,
so I could give some answer to that if you allow me, Jan.
Yeah, sure.
So depending on the adduct, So some adducts will give you like a similar spectrum, but then obviously from a different kind of pseudo parent ion. But if you take, for example, the sodium or other salt adducts, they will usually hardly give you any fragment peaks, because most of the charge remains on the salt part of your adduct, and hence you don't see any fragment peaks, or not a lot. So.
Yeah, so that's actually very true. If you by mistake make the MSMS on an adduct, you will often see that you see nothing at all.
Yeah. So how to minimize the fragmentation in the ESI source?
Yeah, that's also something that I don't think I would be able to explain. You can play with the voltage, of course, but the question is also, do you want to minimize fragmentation? Because you can get a lot of information for free, you can say in this way, if you use tools like camera. So you can use camera, and then you get a lot of fragments before you even have to go do the MS2 experiments. So, I mean, I understand the question, but I'm not sure that even if it was possible that I would actually do it.
Okay, thank you.
I don't know if you have any other comment on that.
Sorry?
I don't know if you have any other comment on that.
No, other than that, you can play with voltage, you can play with the gas flows that you have available. However, it's often a compromise between sensitivity and you know, also number of fragments and things like that. So you might be able to reduce it, but then very likely at the cost of a drop in sensitivity. So
yeah.
So then there's the question here: are there any further advice for GCMS analysis?
Any further what?
Any further advice? I'm just you know, repeating the question as it's stated here.
No, not from me at least. I've not really worked with GC, so I can't.
No, so I'm sorry.
But identification is a lot different there. If you have classical electron impact, there you rely really a lot on the NIST library, because there you often don't see the pseudomolecular ion. So doing that from scratch is very, very difficult.
Yes. So. Yeah, and we hope in the future that we can organize an EMN webinar on more targeted on GCMS analysis and the identification challenge. And then we have, I think, let's make the final question for today, which is a simple one to answer. What was the link from the last slide again? I'm not sure which link exactly is meant, but at least
I assume the one to my website, because then you can at least find the slides with all the links.
So maybe we leave this slide open for another 2 minutes, and then I think we discussed all the questions that were asked, yeah. With that, I want to thank you very much for your very nice overview of compound identification on the basis of LCMS features. And I hope that all the attendees enjoyed the webinar as much as I did. And with that, I will leave the slide open for another minute, and then wish you all a very good afternoon, morning, or evening.